kinetic energy depends on mass. And as before here, we have to ask again the same question. Physically, what does this mean? Well, physically, we say that it's going to be easier to make a car go, how do I say this? Go fast. So if it, I'm going to do this here. I'm getting stuck on my words here. So it's easier to make a car go fast. It's harder to make a truck go fast. So because it's easier, we then say that you have a smaller work. Or in other words, you have a lower kinetic energy. In this case, you have a larger work, so therefore you have a higher kinetic energy. So how much work is required is the exact same as talking about kinetic energy. So let's draw those pictures all over again. So physics-wise, how do we see this here? Well, let me go back and steal from this picture right here again. And just say that we have this scenario as before. So I'm going to focus on the car. And so we've already analyzed this situation. So what's going to be the big difference here? The big difference here is that I could imagine that I have a truck. So if I have a truck, you could imagine that this truck here is going to have more mass. So when I'm looking at this guy, clearly this truck has more mass than the car. So I could imagine that this truck is going to be moving at the same speed as the car right here. But what's got to be the big difference here? The big difference has to be how hard you have to apply. Because it's larger, you're expecting that you're going to have to apply a larger external force in order to do this displacement. So if I have this scenario here, you could imagine that if I take my truck again and I copy it, and let's say that we have now pushed this truck so that it now has the same speed as the car. And we did this over the same displacement here. Then picture-wise, what do I actually see here? Again, I want to make sure that you're still seeing that there's still an external force applying on this big truck as it moves here. So now, what do I see here? From a bar diagram standpoint, each car has the same speed, we got to be careful here. If this car has the same speed as the truck initially, it's got to be K1. But note that for the truck, it has to have a higher kinetic energy. The truck has to have a higher kinetic energy because if it's going the same speed, its mass is going to be larger. So now I'm going to look at how much work is being done. This is the amount of work that was required to change the speed of the car. It was easier. But for the truck, it required more external work. So as a consequence, this car does get an increase in kinetic energy, but the truck increases its kinetic energy considerably more. And the reason why there's a higher kinetic energy is because there was more work. This has a smaller change in kinetic energy and requires less work. This has a higher kinetic energy and it requires more work. So once again, we have the same picture as before. In the language of the work energy theorem, we then say that the car had a small external work. In other words, it was easier to get to speed V2. The truck had a larger external work. And then we say that it was harder to get to speed V2. So then the reason why it was harder is because we knew that the external forces were going to be different. So instead of saying easier or harder, we then say that this had a lower change in kinetic energy. This guy had a larger change in kinetic energy. And why was it larger? Because in this case, this one had a smaller mass, and in this case, this guy had a larger mass. So even though they reached the same speeds, we can see here as that it was the large mass dependence that caused this. That's what we mean by kinetic energy right there. Okay, that's what we mean by kinetic energy. So what I'd like to do here is that I just want to say two more things that are related to each other. So I don't know what step this is. I think I'm on 3. So let me see if I can just finish up kinetic energy. Because once we do kinetic energy like this, then will move quicker through potential and thermal energy because it's the same type of thing. So here's a question. Which requires more work to catch? A bowling ball or a baseball with the same kinetic energy, same change in kinetic energy. So which would require more work? And the answer is neither. Because if I say that the change in kinetic energy of the bowling ball is equal to the change in kinetic energy of the baseball, if these guys are the same, then that implies that that means that they have the same required work to stop.
Does this mean the baseball is just moving a lot faster then?
It
To make
has
up for
to
the
be
weight?
moving a lot faster. And the only way you can do this here is that if we're going to stop it, then that means that the final kinetic energy of the baseball must be zero, and the final kinetic energy of the bowling ball must also equal to zero. So then when I look at the change in kinetic energy of the baseball, this should be K2 minus K1. So this should be 0 minus, and then we can see here is that the mass has to be smaller. But if I look at the kinetic energy of the bowling ball, that has to be 0. But then this mass has to be larger. So the only way that these two are going to be equally have the same work is that if this guy initially has a large speed, whereas the bowling ball has a lower speed. That's the only way that these two can have the same amount of work. So they can only have the same work if the baseball is moving faster than the bowling ball. Now, exactly how much it's going to have to depend on the ratio of the masses here.